Okay, here are the sample problems for Math 117 Class 10. And the first of these is yet another exercise in explaining weird notation from Deneen. So, I've created a graph of a random variable, and this graph is sort of wiggly. And the task that I have set for myself is to construct the inverse image of the event which Deneen calls I super 2 sub 1 comma 0, where symbols have the following meaning. I'm talking about I super 2. That 2 means we have 2 squared, or 4 subdivisions. And the lower subscripts 1 and 0 are j and k respectively. And we're also given that m equals 1. So what does this all mean? Well, m equals 1 means that the random variable is bounded above by 1. Okay. N equals 2 means we use 2 to the n, or 2 squared, or 4 subintervals. So that means that on the vertical axis, we take the interval from 0 to 1, and we break it up into 4 equal subintervals, one going up to 1/4, one going from 1/4 to 1/2, one going from 1/2 to 3/4, and the last one going all the way up to 1. Here is our graph. Doing my best to draw it freehand by actually tracing over a copy of the printed page. Okay. K equals 0. Means that we look at the interval from 0 to 1. If m were larger, then we could have larger values of k. If m were, say, 7, we could look at the unit interval from 3 to 4, and these are always, closed at the low end and open at the high end. And then j means we look at the subinterval that goes from k equals 0 plus j equals 1 over 4 up to k equals 0 plus j plus 1, which is 2 over 4. In other words, we want to focus our attention on that subinterval. Okay, what's the inverse image? Well, there's a range of values for omega where the random variable has a value between 1/4 and 1/2. Coming down, we've got another one, like that. Then, as we go back up again for a while, we are in between 1/4 and 2/4. And here, finally, we come down below 1/2. And there's the answer. The answer we want is the union of, in this case, 4 intervals. And since the interval in the codomain is open at the upper end and closed at the lower end, whenever we have the upper end, we have an interval that's open. So this interval is completely open, but these other 3 are closed at one end, open at the other. And all that really matters about this is that it's a Borel set. So this is the fundamental idea behind Lebesgue integrals as presented by Deneen. You break up the codomain into intervals that are bounded by a pair of fractions where the denominator is a power of 2, and then the inverse image in the domain in general is going to be a union of intervals, but because every interval is a Borel set and the Borel sets form a sigma field, any countable union of such intervals is also a Borel set. Problem 2 is quite different. And I can't find an example like this anywhere in Deneen, but I think it's very important to make the point that with the Lebesgue integral approach that you're learning, you integrate over the codomain, not over the domain. So here's an example that I've dreamed up. The sample space is two-dimensional. It's a square of side 2. Let's call the coordinates u and v. And the random variable is the distance from the line on which u and v are equal. Sorry, I'm having just the worst time with this tablet. So there's the line. It's just a total mess. I'm going to blank the page and try again. Okay. Let's have another shot at this. Okay, here's my square of side 2. A little better. on this try. There is the line where u minus v is equal to 0. And now I can define my random variable. Capital X of omega. Omega is a point in this plane, and the random variable is the distance from the line where u minus v is equal to 0. So, for example, on that dotted line, the value of the random variable is that distance x, and if you look down here, you see there is x, and there is the hypotenuse of a little right triangle, the square root of 2 times x. But there's an extra rule. The extra rule is that the value of x cannot exceed 1 over the square root of 2. So down in this triangle, x has the constant value 1 over root 2. And similarly, up in this triangle, x has the value 1 over root 2. So now I have to work out p sub x, the probability of the value lying in the interval from 0 to x. Which is usually written just as a function of little x. Okay. By the rule I just stated, if the random variable has the value 1 over root 2, then the probability of that event, and that should really be a lowercase x, the probability if x is greater than or equal to 1 over root 2, the probability of being less than that value is 1. If, on the other hand, x is less than 1 over root 2, then the probability that capital X has a value less than or equal to that little x is 1/4 times the area between the two dotted lines I'm about to draw, for which the distance is little x. One of them is already drawn. Here's the other one up here. So you get the idea? I pick a little x. If little x is less than 1 over root 2, then since the probability of being in a region of this square is proportional to the area of that region, the probability is equal to the area of this region divided by 4, the total area of the square. Okay, working that out is elementary geometry. I have 1/4 times the total area, 4 minus twice the area of one of these triangles. So the area of one of these triangles is a half of 2 minus root 2x squared. Fair enough. The triangle has that side. It has that side. Its area is 1/2 the product of the two sides, but I've got two triangles, so I can drop the 1/2, and that's going to give me 1/4 of 4 minus, multiplying this out, 4 plus 4 root 2x minus 2x squared, or finally, I've worked it out. The probability that the random variable capital X will have a value between 0 and little x is equal to root 2x minus 1/2 x squared. And I can do a quick check on that. If x is equal to 1 over root 2, then I get root 2 times 1 over root 2 minus 1/2 times 1 over root 2 quantity squared is equal to 3/4. In other words, the probability of being less than or equal to this is 3/4. The remaining probability, 1/4, is the probability that we're in one of these triangles and have precisely the value 1 over root 2. Now I have to jump ahead in Deneen and calculate the so-called density function. The probability density function, f for the random variable capital X, is just the derivative of the probability distribution function that I found. It's p prime, and by elementary calculus, the derivative of this function is root 2 minus x. And now I can calculate the expectation of x by doing an ordinary integral. But first, I have to take into account the fact that there are two regions on which x has a constant value. The probability of being in one of those two regions is 1/4, and in those regions, the value of the random variable is 1 over root 2. So this random variable has the interesting property that it's got a discrete part. There's a finite probability of 1/4 that it has this specific value, and it also has a continuous part in which I can calculate the expectation by doing an integral. I integrate over all values from 1 over root 2, x times the density function, root 2 minus x, and that's going to give me 1 over 4 root 2 plus the antiderivative here is x squared over root 2 for the first term minus x cubed over 3 from the second term. And I think I got this right. 1 over 4 root 2 plus 1 over 2 root 2 minus 1 over 6 root 2, which I think works out to 7 over 12 root 2. But I don't really care about the answer. All I care about is that we integrated over the range, not the domain. If I were doing this problem in Of course, in multivariable calculus, like Math117SP10, I would set up a double integral over u and v. And that's the way most people learn to do these problems. But we're doing them differently. We're using a definition of integration that basically says generalize from the idea of doing a sum over all the values of value times probability of that value. And that's going to lead us to a Lebesgue integral rather than a Riemann integral. Well, you'll recall that in the last class, the proof involved increasing sequences of random variables. And in this class, you're learning how to create such increasing sequences, so-called canonical sequences. And what I need to prove is that with these canonical sequences, I have an increasing sequence of random variables that approaches my original random variable x. So the first point, random variable x is bounded by some value m. We're still not dealing with unbounded random variables. In other words, x is non-negative and it's less than m. So that means I can break up the set of values into 0 to 1, 1 to 2, k to k plus 1, and everything is bounded by the integer m. And now I can take a close-up view of this. In my close-up view, I'm only going to consider the part between k and k plus 1, and I'm going to break that up into 2 to the nth pieces, and here is a representative little piece. It starts at k plus some numerator j over 2 to the n, and it extends up to k plus, you guessed it, j plus 1 over 2 to the n. And now, if I consider some point in the sample space, omega, that leads to a value in this region, that is in the inverse image of the interval that starts here and extends up to, but not including, the upper limit. I just define the random variable x sub n for that omega to be equal to the value at the lower bound. In other words, the way I form x sub n is for each of these subintervals, what I do is not use the true value, but rather the value at the lower bound of the interval. There are only finitely many such values, and therefore each x sub n is a simple random variable, even if x itself is not. And in doing so, I can't change the value by very much. The most I can do is change the value by the size of one of these intervals by an amount that is less than 1 over 2 to the n. Okay. Now what happens if I increase n by 1? If I increase n by 1, I have k plus j over 2 to the n down at the bottom. I have k plus j plus 1 over n over 2 to the n at the top, and smack in the middle I have k plus 2j plus 1 over 2 to the n plus 1. And now there are two possibilities. It could be that omega leads to a value in here. In that case, what I did originally for x sub n was to round it down to that value. And what I still do, even when n is 1 greater, is round it down to that same value. So in that case, x sub n plus 1 of omega is equal to x sub n of omega. But if omega led to a value in the top half of this subinterval, in x sub n, I rounded it all the way down to there. In x sub n plus 1, I only round it down to there. And so in that case, x sub n plus 1 of omega is greater than x sub n of omega. And I'm done. That means for all omega, x sub n of omega is an increasing sequence. And as n approaches infinity, these intervals get smaller and smaller. The difference between x sub n and x becomes smaller and smaller, and therefore this sequence, which is increasing, converges to its least upper bound x of omega. And that completes the proof.